And that what I want to do with this presentation is talk about research tools that I have and kind of my own personal approach to thinking about things, kind of in the spirit of the collaborations that are going to happen over the next several weeks, so that in, say, 2 weeks when you're starting to work on your projects, if you run into a problem and you think, I could really use somebody that does blah, or I could really use a tool that does maybe I'm the person that does blah or and so you can come talk to me. Okay, so the things that I work on kind of fall into 4 different categories. I do exoplanets and brown dwarfs. I do mission-oriented stuff, as I talked about yesterday, specifically related to W1st and HABEX. I'm interested in solar system planets, and I do some work on those. And then, having come from an astrobiology program, I still maintain some keen interest in that, and so I do a little bit of work or thinking on habitability. So I'm going to kind of touch on these different points and let you know kind of what tools I have that you could come talk to me about that you may find useful. So one of the things that I like to do is I like to look to the solar system and find analogies in the solar system for things that we might observe or Okay, I'll keep going. So we picked Titan because Titan is the quintessential hazy world in the solar system, so we kind of wanted to know what a hazy planet in the solar system looked like in transit, so I'm moving along quickly. So these are the transit spectra that we got for Titan. And so Cassini repeated these observations on 4 separate occasions, and so I'm showing you those 4 different transit spectra that we derived. Because the reason why I'm showing you those is because it demonstrates that, as Jonathan said earlier on, he thinks planets are very difficult, and this shows that planets aren't spherical cows, that depending on what latitude you're looking at on Titan and depending on what time of year, the haze varies, and so you get different transit spectra for those different latitudes and times of year. So I'm plotting this as effective transit height, which just scales with the transit depth as a function of wavelength through the near infrared. You see plenty of strong methane bands, which is because methane is very abundant in Titan's atmosphere. For some of the more wimpy things like acetylene, they do poke up a bit above this continuum that's set by the haze. And I'll just hang on to this, I guess. If this works until it dies, or it doesn't die, then it'll be fine. Okay, and then maybe we'll have to switch again. So we fit an analytic, it's just a 3-parameter model to the haze continuum to try to back out from that transit spectrum some of the physical properties of the haze in Titan's atmosphere. And so the parameters in that model were just a haze scale height, a power for the power law dependence in the absorption cross-section of the haze, and also an optical depth of the haze. And so that dashed line there is the fit that we derived, and there's a Rayleigh scattering curve on there too, just to show that it's not Rayleigh scattering that's happening in Titan's atmosphere, it's me scattering. And so the haze scale height, the optical depth, and this power law extinction coefficient that we derive from the transit observations are actually very comparable to what Huygens got with the in situ observations, which I think was really powerful because that says that in transit observations you have the potential to back out information about the atmosphere to a quality that's similar to what you get in this case with in situ observations. Switching again. Can you hear me? Okay. Another thing that I do is model spectra of the pale blue dot. And so if at any point in this week you need a spectrum of the Earth that you can trust, come talk to me. So maybe you're interested in detectability or biosignatures or something, I can supply you with a spectrum. The tool that I built and use is called the Virtual Planetary Laboratory 3D Spectral Earth Model, and those are some simulated images from the model. And really what it does is it makes a high-resolution, phase-dependent spectrum of the pale blue dot. And so I'm showing you a spectrum here from the UV through the thermal infrared, so it includes both reflected light and thermal emission. So depending on what wavelength you may be interested in over the next few weeks, I have a spectrum for you. And so one thing that you might be interested in doing is, say, looking at what LUVOIR observations of the pale blue dot might look like. And this is a simulation of what LUVOIR could do for an Earth-like planet around a Sun-like star at 10 parsecs. And so maybe if you're working with Mark or talking with Mark because he's on the LUVOIR STDT, this is something that you might be interested in. I mentioned that I'm interested in exoplanet-oriented missions, and so Mark has already given an introduction to WFIRST, and so Mark and I are both on one of the WFIRST science investigation teams. And so we concern ourselves a lot with characterization of exoplanets and reflected light that the WFIRST might be able to do. And so a tool that I have that is both online and I'm happy to share with you all and tell you all how to use is a noise model for WFIRST that Mark and I put together. It includes kind of all the essential things that you would want to include in such a noise model. So it has the planet signal, so you need to give it a reflectivity spectrum of your planet. You need to give it a stellar spectrum for the host star. It includes solar system zodiacal light. It includes exozodiacal light. It also includes read noise and dark current. And so from that, you can get a noised up spectrum as WFIRST would observe your planet in reflected light. So one thing that you can do with this noise code, and that Mark, myself, and Carl Stoppelfeld did do this year, was we looked at how well WFIRST would be able to detect certain species for certain types of exoplanets. And so in this case, I'm going to show you right here is what I'm going to call, I'll call it a cool Jupiter, but really it's a Jupiter who's receiving an amount of radiation that's a little bit below what, say, Mars is receiving in our solar system. So warmer than our current Jupiter, but not a hot Jupiter. And so what I've done is I've put that Jupiter at the same flux, equivalent flux distance around stars of different effective temperatures. And then I've put those systems at different distances from us and looked at how long would you need to stare with WFIRST to detect methane. And so the band that I used, if you look here at the lower right, is the 0.73 micron methane band. And so then contours, the color contours are in integration time that you would need to detect that band. In this case, it's signal noise of 5. And so if you consider that you're going to have of order hundreds of hours to do exoplanet characterization with WFIRST, and you don't want to spend all of your time on one target, then you're probably looking at wanting to spend about 10 hours or so on any individual target, which means if you come down here, that you'll be able to do that out to distances between about 5 and 10 parsecs are the kinds of targets that you're going to be looking for. I do a lot of model construction, and so I've worked with actually many of you in the audience before doing radiated transfer, and so a lot of you know that I do radiated transfer and opacities. So at any point in the next several weeks, if you need opacities, or maybe if you need a spectrum of, say, like I said, Earth or Venus, you can talk to me. So I can be one of your opacity go-to people. And then so on to actual results of things that I'm working on right now and I've been interested in is I've been building a tool for simulating transit spectra of exoplanets. And so I have tried to include a lot of physics in that tool that aren't in standard exoplanet simulation, exoplanet spectra simulators. So Mike Line has been very kind to me and has been helping me get this tool up and running. through doing intercomparisons with me. And so at this point, this is for an isothermal atmosphere around a hot Jupiter-like exoplanet, 1500 Kelvin. His model and my model are in good agreement. And what's nice about this is we're not using the same opacities, and we're not using the same forward model, and we're getting a very similar answer. So that's actually really nice. So the stuff that I'm about to show you right now is unpublished and is in prep right now, and just want to attach on a little caveat here that my slow brain is still at work on these, and so it's definitely a work in progress. So with my simulator, one of the things that I wanted to include was multiple scattering. And so now I can look at the effects of scattering on exoplanet transits. And so this is a simulated image of a hot Jupiter-like scenario where I've put it on the limb of a star. The star is limb darkened. Because the center of the star is so bright, I've turned up the contrast a little bit off the disk of the planet so that you can see that there's a forward scattering haze in that exoplanet atmosphere. And so the first question I want to ask with this model is, when does scattering matter? So in most spectral simulators for exoplanet transits, you just assume that scattering optical depth is equivalent to absorption optical depth. But maybe that assumption doesn't always hold. And so what I set out to do was kind of make idiot-proof plots for myself, where I tried to trim down to the fewest number of parameters that you would need to define whether or not scattering matters or doesn't matter. Okay, almost done here. And so you can actually, I might not need the bonus minute. So you can actually distill this down to 3 key parameters. One is the angular size of the star as seen from the planet, because that defines essentially the size of the target that you want to scatter photons back towards when those photons are scattering through the atmosphere. If you're thinking about tracing a ray back from your eyes here on Earth through the planet atmosphere and trying to hit the stellar disk. It depends on the scattering optical depth of the cloud. And so here I'm assuming just a thin layer of cloud in the exoplanet atmosphere. And then it also depends on the asymmetry parameter, the scattering asymmetry parameter for the cloud particles, where I'm plotting this as 1 minus g to highlight the forward scattering regime over here. So obviously, very forward scattering particles are going to do a very good job of tracing almost straight back to the stellar disk. And so I've set this up to be kind of hot Jupiter-like. So this would be something that's like 0.05 AU from a sun-like star, to put that in perspective. And so by running my transit spectrum simulator, I've been able to map out essentially the difference between, for a single annulus on that planet's disk that has a cloud in it, I compare the transit depth that's computed if you include scattering to the transit depth that is computed if you treat scattering as just absorption. And so you can see then that in the forward scattering regime that you can get very substantial differences in the transit depth that you compute for that layer as a result of multiple scattering. And so there are situations where multiple scattering is important. And like I said, this is still something that I'm working on. And so the next step is to show some spectra where multiple scattering is important, and to do a little bit more thinking about what kinds of situations you might find yourself in where multiple scattering can be important. Okay, so I'm just going to go back to this and say, if you have questions about WFIRST or HabEx, talk to me. If you have questions about, say, opacities or spectra of brown dwarfs or exoplanets, I'm one of actually many people in that case that you can talk to. If you want to talk about analogs in the solar system for exoplanet processes, I'm really excited about that. Please come talk to me. And then I'm always interested in talking about habitability. And so you could talk to somebody like myself or call in about that. And with that, I'll say thank you. Well, so it'll depend on, so what I've been trying to do is not dip into microphysics with this project, or trying to relate specific kinds of clouds to the parameters that I'm using. So in those plots that I was using, I tried to distill it down to the fundamental parameters, which is the asymmetry parameter and the cloud scattering optical depth. That said, at visible wavelengths, Things like water clouds in Earth's atmosphere are very strongly forward scattering. Hazes at, say, the 1 micron particle size and at visible and near infrared wavelengths can be as forward scattering as what I'm talking about there, so Titan-like or early Earth-like hazes. And so there are plenty of examples in the solar system that you can point to where you do get that kind of strong forward scattering. And almost all things are forward scattering. The question is, how strongly forward scattering are they? Coffee. And what I want to do with this presentation is talk about research tools that I have and kind of my own personal approach to thinking about things, kind of in the spirit of the collaborations that are going to happen over the next several weeks, so that in, say, 2 weeks when you're starting to work on your projects, if you run into a problem and you think, I could really use somebody that does blah, or I could really use a tool that does maybe I'm the person that does blah or and so you can come talk to me. Okay. So the things that I work on kind of fall into 4 different categories. I do exoplanets and brown. Observe or okay, I'll keep going. So we picked Titan because Titan is the quintessential hazy world in the solar system, so we kind of wanted to know what a hazy planet in the solar system looked like in transit, so I'm moving along quickly. So these are the transit spectra that we got. Dwarves. I do mission-oriented stuff, as I talked about yesterday, specifically related to W1st and HABEX. I'm interested in solar system planets, and I do some work on those. And then, having come from an astrobiology program, I still maintain some keen interest in that, and so I do a little bit of work or thinking on habitability. So I'm going to kind of touch on these different points and let you know kind of what tools I have that you could come talk to me about that you may find useful. So one of the things that I like to do is I like to look to the solar system and find analogies in the solar system for things that we might